Hello. We've got this idea of these stabilized target detections, and we're going to now want to have a way of describing what we actually see with these stabilized target detections. And also before that, actually, we'll just do a little bit of formal description of how we can get those stabilized targets as well too. The general process of what we're going to look at is really has these three components. Okay, the first is we're going to stabilize that target, so we're going to look at an algorithm for doing that. Second, we're going to compute the optical flow, and we're not really going to look at an algorithm actually for doing that. That's a kind of standard algorithm that one could look up in a textbook. But we'll see sort of how it performs based on our kind of data here. And then the third thing we're going to look at is how to take that optical flow and turn it into a kind of descriptor that we can use for doing the matching of the behaviors. Okay, so how are we going to do this target detection and image stabilization? Well, the first step is we need to find out where the targets are. And the way that we can do this here is just by subtracting consecutive images. We're assuming that if the camera is stationary or reasonably stationary, that where targets are moving, there will be a reasonable change in the background. And that will give us some idea of where the target is before and after that we want to detect. Now we're going to want to do a little bit better job with the stabilization than just put a box around where the changes are. So that's where the next step is going to be. And the basic idea is we start with a box and we're going to kind of try to correlate the image data. Assuming that the person that's moving doesn't change too much in shape, we're going to sort of start with the boxes and we're going to match them around, move them around until they do their best job of matching. And once we've done that sort of correlation type activity, that's going to give us the prediction of how these boxes should overlap with each other. And that will give us one box to the second box, and then we can do the second box to the third box to the fourth box, etc. And that will give us a stabilized type of descriptor. Okay, so what we want to do is we're going to do this maximum correlation kind of thing, and that'll give us the translation or whatever that maximizes that correlation. Well, how can you express that more formally? Well, that's what we've got right here. So this is our scoring type function, and we're going to do this by effectively a correlation of over all pixels in the region of interest in the first image, and indexed by its row and column in the current time, and we have sort of the mean of that bounding box. So that's the mean of the bounding box. The first image here is the bounding box in the second image with the sort of time t+1, again the mean subtracted, and these are the corresponding pixels but adjusted by that shift here dc dr that we're sort of exploring. We're trying to find the dc and dr that maximizes that correlation. And we also have to do a bit of normalization by the standard deviations, and that's what these two factors are right here. So I've given sort of all of the formulas for doing the details right down here. I'm not going to go through all the formulas, but that's the basic idea. Is we're going to do a cross correlation between the two image boxes to try and maximize the matching, and that will give us the offset that allows us to align all of our little individual frames together to stabilize the image. And that's what gave us this sort of mosaic of all these stabilized runners that we saw previously. Well, that's the first stage. That gives us a stabilized sort of bulk translation of the object, but the individual people still have their internal actions, sort of their arms moving and their legs moving, and we want to now look at how we can analyze that. Well, the next step here is is related to that, and that's what's called the optical flow. This is a kind of measure of how pixels are moving in the image and gives us an idea of a flow. Most of the time, people encode that with a little vector. So here's an example image taken from a video, a street scene, and so we've got a car right here that's sort of moving this way. There's another car coming into the scene. There's another car moving through the scene right here. And what you can see is a kind of a representation of the optical flow where at selected pixels, not every pixel, but every sort of 5 or 10 pixels, you can see a little vector in here. So you can see, like right about here, you can see a little straight line with a kind of diagonal little line on it. Okay, and that's vector which says that there's a lot of movement in this particular place and it's moving in this direction. And that's what you would expect to see from where this vehicle is moving in this particular direction as it goes around the corner. So it's a kind of, it's a method, optical flow is a way of encoding the motion that's happening in the image at every single pixel in terms of both how much motion and what's the direction of the motion. And so that's the image velocity, UV, sort of the horizontal and vertical components of that image velocity. So there are standard algorithms for estimating this optical flow, and we're not going to look at that. So when we get to our sort of our football scene, here's our stabilized image. We're going to use a couple of these consecutive images to calculate the optical flow. And here's an example of one of those images, and here's the excuse me, the optical flow overlaying on top of that sort of image. And you can see that there's a lot of sort of big vectors down here as the player's sort of knee and leg are moving quite quickly. Similarly out here at the front with the player's knee and leg as well. And also some related to the arms. But you also see there's almost no motion with regards to the background. That's what you would expect. It's more or less been stabilized. And, you know, sort of head and belly and stuff like that, there's not too much motion. There's a fair amount of motion on the waist as they're moving forward quickly as well. So you see this gives us a kind of pattern of motion around this object. And the assumption we're going to make is that whenever a person is doing their sort of run in this particular pose, they'll have a similar pattern of motion. And that kind of makes sense because, you know, if it's repetitive or whatever, you just sort of see the same motions and therefore you get the same optical flow. Okay, so that's going to be our optical flow, and now we want to somehow create a descriptor that tells us a bit about how to encode this so we can match that optical flow when we see it again. Well, the first thing we can do is we can take that two components of the optical flow and we can separate them out into the vertical and the horizontal components. So here's a kind of grayscale encoding of the horizontal components. And so this is the U is the horizontal, the V is the vertical. And you can see here, so it's quite bright here, so that means it's moving very quickly in one direction. Here's quite dark, it means it's moving quite quickly in the opposite direction. And then there's sort of neutral grays in here, which says that it's not moving very much in the horizontal direction. Similarly, here's the motion in the vertical direction, and you can see some bright spots and you can see some dark spots. Well, one of the things that we notice about this is it's a little bit noisy. And typically when we have some sort of measurements that are noisy, we want to do some sort of noise reduction or smoothing on that. But unfortunately, if we did smoothing on this, this is going to erase some of the data that we want. So we have, you know, for example, we've got a dark spot quite near all these light spots. And if we did some averaging right here, it's going to turn into this sort of neutral gray of the background. We're going to lose the information that we want. So that's where the authors, researchers who developed this technique came up with another idea. And they said, well, rather than working with the U component, the V component, directly with both the positive and negative elements there, what they can do is they can split that data into the positive bits and into the negative bits, and then they're going to smooth them independently. So basically what it comes down to is that they've got a function f right here that basically says take that U and V and turn it into four components. Okay, sort of the positive component, the negative component of the U, the positive component of the V, and the negative component of the V. Okay, and represent those independently. So if we go back and look at our image right here originally, now when we break that up into the four components, we get something like this, sort of the negative and positive components of the horizontal, and similarly for the vertical. This still looks noisy, but now at this point when we do that smoothing, we can kind of average away the noise in the data without destroying the relationship between the positive and the negative components. And that's what we get next is an example of something like this. So here the researchers just use Gaussian smoothing, sort of the normal convolution with a Gaussian distribution, two-dimensional Gaussian distribution in this case. So that just kind of blurs things around a little bit, but you can see that it leaves sort of kind of clearer sort of lumps where action is taking place without all of the sort of the minor little details that we have right here, which are a bit noisy. So that's kind of given us a more sort of stable type of descriptor. Well, we do this for every one of the frames, and each of the frames, we may have 50 of them. They use 50 in their particular example. So they took this sort of center frame plus or minus 25, or 24 thereabouts, to get a total of 50 frames. And for each of those frames, they took the optical flow, and then they split it up, and then they smoothed it. And that's what they came up with for their descriptor. So we can represent this a bit more sort of formally, just saying for every pixel x, y in our descriptor, so that's sort of x and y right here, and then we have each of the 4 optical flow components that we looked at with the 4 things, and then we have each of our frames right here. We get a descriptor. It's quite a large descriptor, but it gives us some idea of what action is taking place inside the bit of image that we're looking at that particular time. Okay, so that gives us quite a rich sort of descriptor that takes account of sort of some subtle variations. It can make the distinction between sort of going like this, the 2 arms going like this, or arms going like that, because they're at different depths, and sort of other little actions. Even though the arms may be more or less in the same position, they can make a distinction between those. Okay, so that's quite useful, and we'll see how that works in just a minute. Unfortunately, this is view dependent, as I've said previously. So this action of a person making a motion like this would look very different than if they were making the motion that looks like this. Although it's the same 3-dimensional motion, the descriptor that we're storing here is relative to the camera. And so if we want to look at people in different positions, we would have to do recordings from different viewpoints. Right. Thank you.